Hey guys, today's video is kind of a continuation of what we were discussing the other day. And again, there's going to be some connections between the math that you've probably been learning about in math class and the real world applications that we use in physics. So this is where we're going to start here. We just have a line here. It says find the slope between these 2 points. Now, just like last time, let's pay attention to what's actually being graphed here. And so we can see on the y-axis we have velocity, right? Presumably in meters per second. Meters per second. On the x-axis we still have time, which is going to be in seconds. And time is pretty much always going to be on the x-axis, as we discussed last time. So find the slope between these 2 points. Well, first, maybe it's useful. It's pretty obvious. Obviously, it's just delta y over delta x, y2 minus y1 over x2 minus x1. Sorry, that's really sloppy, but hopefully you're following me here. So the change in y, so y is the second point, so it would be 14 minus 8 divided by 6 minus 3. 14 minus 8 is 6, I believe. 6 minus 3 is 3. So we quite simply get 2 as our slope. But that's not very useful. You can probably already guess what we're going to do. We're going to put in the units and let's see what happens. So once again, instead of this being 6 comma 14, it's really 6, that's x comma y, 6 seconds, comma 14 meters per second. And then this, of course, will be 3 seconds, comma 8 meters per second, because those are velocities on the y-axis. Okay, so if I just replace this on top, I'd have 14 meters per second minus 8 meters per second divided by 6 seconds minus 3 seconds. On top, we still get 6. Now we get 6 meters per second divided by bottom 3 seconds. And we did this in the last video, so I won't go over again. But if you do meters per, so obviously we get 2. But if you do meters per second divided by seconds, you get meters per second squared, which of course is a unit of, this must be acceleration. I didn't quite have enough space for that N. That poor N there just fell off. So we just discovered here that at least the units have told us, and again, that's why we focus on units so much, because they can tell us a lot of information. The units have told us that if I have a velocity versus time graph, right? Remember, that's how you always name these graphs. It's always the y-axis versus x-axis. If I have a velocity versus time graph, the slope on that graph is the acceleration. And you can add that to your notes there. So again, I'm not spending a whole lot of time on that because it's pretty much exactly what we did last time. Last time we had displacement versus time graph, and we discovered that the slope on the displacement versus time graph was velocity. Well, this time we've discovered on a velocity versus time graph, the slope is the acceleration. So in this example, I'm not going to solve the problem. I'm just going to point out, if I want to find out what is the acceleration at 6 seconds, I simply need to look at, presumably this is 6 seconds here. I just need to find what is the slope from 0 to 6 seconds, if that's what I need. All right. Well, what can this tell us? Can we infer some other equation from this? And of course we can, because if it's a line, right, we have y equals mx plus b. So once again, if I have just some rudimentary, okay, this is going to be a velocity versus time graph. If I have some line that goes through like this right here, well, this line has the equation y equals mx plus b. So let's take this specific equation here, or this general equation for a line, and turn it into a more specific equation for a line on a velocity versus time graph. So instead of y values, right, the y values are velocities. So velocity is going to be, m is the slope. So whatever the slope is here, but as we just discussed, the slope on a velocity versus time graph is the acceleration. Acceleration times x is the time, plus the y-intercept in this case is going to be a velocity. And you can think of this as the initial velocity, the velocity at time 0. So on the x-axis at 0, that's your initial velocity. And so we get this equation here, that the final velocity, the velocity after some object is accelerating, is going to be the acceleration times the time plus the initial velocity. Okay, so can we apply this? Let's see. It says here, Ruben throws a ball straight into the air with a velocity of 15 meters per second. The acceleration due to gravity is negative 9.8 meters per second. Uh-oh. That should say, and I'll have to change it on the slide. Whoops. That should say meters per second squared in order to be a unit of acceleration. I'm sorry about that. So acceleration due to gravity is negative 9.8 meters per second squared. What is the velocity of the ball after 3.8 seconds? So let's see if we can figure out how fast the ball is moving after 3.8 seconds. So we just are going to apply that equation we just saw here. Velocity, the final velocity is going to be the initial velocity plus acceleration times the time. And I know I did that backwards. It obviously doesn't matter what order you do that in, since you're adding, it's not going to matter. So the velocity is going to be, the initial velocity here was 15, it's going up, remember up, and these are all vectors, right? Velocity is a vector, acceleration is a vector, time is a scalar. But since it was going up, that's positive 15. That's why this acceleration due to gravity is negative 9.8, because it's going down, it's a vector. Plus negative 9.8 times the time is 3.8 seconds. And look what happens here. Let me just quickly, meters per second, right? This is, I should have written this out better. Meters per second squared, and these are units of seconds right here, right? Because it's just 3.8 seconds. Look what happens to the units. These seconds cancel with one of those, and I'm just left with meters per second. So once again, just reaffirms, if I take an acceleration, I multiply by time, I get a velocity back out. So my final velocity is going to be, I'm going to pull out the calculator here, 15 plus, in parentheses, negative 9.8 times 3.8. And the calculator tells me the final velocity is going to be negative 22.24 meters per second, which is pretty fast. Again, you can put that into Google and figure out how fast that is in miles per hour. But that makes sense, right? I mean, think about it. You throw a ball up in the air, it's probably going to be moving pretty quick after 3.8 seconds. Because obviously gravity is going to accelerate that object. Okay, so there's the equation, like I said, we just got. Okay, real quick, I want to look at this right here. So this is an object that we can tell, just because this is a velocity versus time graph, this object is not moving, right? It's moving at a constant velocity the whole time, but it is moving. So if I were to ask the question, how far does this object move, right? You can think about this as sort of, you may remember when we did speed, right? To find the distance an object moves, we took its speed times how long it moved for. So in this case here, how fast is this object moving? Well, again, these coordinates here are, this is 2 seconds, because that's time, comma 5 meters per second. So it looks like it's going 5 meters per second the whole time. Great. So that's its speed, so 5 meters per second, times how long did it move? Well, it went from 2 to 8, so that's 8 minus 2 is 6 seconds. So you would do 5 times 6 seconds, and you would get 30 meters. Okay, so and I swear, I make slides, and then I don't remember to make a slide, so, well, yeah, I'll just talk this out. Sorry, it would be better if I wrote it out, but I don't have the slide prepared and I want this to be quick. So basically I found the displacement of this object is 30 meters. Well, what is just out of curiosity, what is the area of this rectangle? What's the area of this rectangle? Well, it's pretty easy to find, right? You would do the height, the length times width. So length, and again, it doesn't matter which one's length and which one's width, just this side times that side. And what would that be? Well, that would be from here 2 to 8, that's 6 times 0 to 5 is 5. 6 times 5 is 30. So you get the exact same thing. You know what? I've decided I'm going to pause this so I can make this slide real fast, and then I'll come right back so I can show you this. Okay, I'm back. Sorry about that, but here it is. So what I was trying to say is, right, what is if I want to know what's the area of this rectangle here, and again, you'll see why obviously in just a minute, but let's say I want to know what the area of this rectangle is. It's just length times width. So in this case, it would be from here to here, right? It would be this side in this green length here, multiplied by this blue length here. And that'd be it. I'll find the area real fast. The area in this case would be, well, it would be this length here. It's this green, which is, well, let's see what that is. That's from 2 to 8. So this is on the x-axis from 2 to 8. So that would be, the total length would be 8 seconds minus 2 seconds. The length of that would be just simply 6 seconds. And what's the height of this? Again, these are on the y-axis, so it goes from 0 meters per second to 5 meters per second. So of course that length is just 5 meters per second. So then the area would be 5 meters per second times 6 seconds. And again, the seconds would cancel with those. You'd have 30 meters. Well, that's a unit of displacement. And once again, we also just determined that if I ask you what's the displacement, right, we can use the simple in this version, speed is distance over time. If we rearrange, we get distance is speed times time. So in this case, how fast was this object going? It was going 5 meters per second, and it went that for 6 seconds. So you get the exact same thing back out, 30 meters. So this is a big conclusion that we can draw from this. We can essentially determine that on a velocity versus time graph, the displacement is the area under that graph, under that function. And we're going to be able to use that to find our big equation, kind of what we're really building up to. I'm going to skip this for now. What I wanted you to see is that if you graph this out, so if this is an object which is accelerating, and if you graph this out, right, if you did a displacement versus time graph for this, right, so the first point would be 0, 0, 1, 1, 3, 2, 6, 3. Actually, I'm going backwards, x, y, so it would be 0, 0, 1, 1, 2, 3, 3, 6, 4, 10. Anyways, you would get, what you would see is you would get this graph that goes up, right, but it starts to curve upwards. And so again, just reaffirms that we have an acceleration, the slope is changing. You get a changing slope, makes a curve. But you'll see that soon. All right, so this is kind of a big info graphic that I made to kind of help you bring kind of all these together. I'm not insulting you here. I'll explain what this is in just a second. If we start with displacement, right, displacement versus time, a graph. To go up on this, right, you take the slope, which in calculus you'll find is called the derivative, but we find the slope or derivative. So if I take the slope on a displacement versus time graph, I move up, that would give me velocity. Likewise, if I have a velocity versus time graph, if I took the slope of that graph, I would go up, that would be the acceleration. So you can see the relationship, right? Displacement is in meters, velocity is meters per second, acceleration is meters per second squared. Now it doesn't stop there. I could keep taking the slope. If I took an acceleration versus time graph and I calculated the slope of that, that would be a different quantity, which is called, and there's really the name for it, it's called jerk. And its units would be meters per second cubed. And it doesn't even stop there. I just stopped because I was kind of running out of space. And then really jerk is about as far as it gets used. There, above that, though, is, and again, not a joke, for real, snap, crackle, and then pop would be even above that. And again, each time you go up, meters per second to the fourth, meters per second to the fifth. Anyways, these are all rates of change, right? Acceleration is a rate of change of velocity with respect to time. How is velocity changing over time? Velocity is a rate of change of displacement. How is your displacement changing? Again, with respect to time or over time. So to go down, right, it's an area, right? So if I have a velocity versus time graph, the slope on a velocity, the area on a velocity versus time graph is the displacement. If I have an acceleration versus time graph, the area on that graph is velocity. So that's how these are related. They're all rates of change of each other. And a slope is a rate of change. Okay, so hopefully that makes sense. There's some conceptual questions that kind of go over that. Before we get to we've got one more kind of equation that we're going to discover for kinematics that'll be incredibly important to us, not only for this unit, but actually for the next unit as well. And I can go ahead and tell you, it's going to be can we calculate the displacement, or how far an object is moved that's accelerating, right? We just figured out, hey, if I try to calculate the displacement for an object, sorry, we did that yesterday, or the previous video. If I want to calculate the displacement for an object that just has a constant velocity, it's easy, right? You just end up with that equation, which I don't have it on here, but the equation like x equals v times t plus xi, right? We figured out that equation, but that was for an object that wasn't accelerating. Can we figure out the displacement of an object that is accelerating is where we're heading, okay? So you've got here, there is an assignment, it's fairly short, and then there's a little practice that kind of just is going to bring a lot of these concepts together. But the big idea here is that we now know, I'd say, the two big ideas. One is that displacement. I'm all over stuff here. Two big ideas. On a velocity versus time graph, the slope is the acceleration. And then the other big one is that on a velocity versus time graph, the displacement is the area under the function. Because we can actually use that, and we are going to use that to derive sort of a large equation that we'll be using in the near future. Okay. Hopefully this makes sense. I know there's a lot of different concepts here kind of tying it all together. But as always, please ask if you have any questions. Thanks.